Welcome to Norton Chemistry. Today we're going to be doing a Hess's Law and Hess cycles revision video. Make sure you stick around for the exam questions, as they'll help you apply your knowledge to exam contexts. Hess's Law says that the enthalpy change for a chemical reaction is independent of the route taken, and this means that if a reaction can occur by two routes, the enthalpy change of each route will be the same. So for example, in respiration, glucose goes to ethanol and carbon dioxide, and this reaction can occur by the first route, which is the normal route, and another route, which is the combustion route. And you can see that in this diagram, route 1 is equal to route 2. And this is essentially what Hess's law means, that if a reaction can take place by more than one route, then each route will have the same enthalpy change value. When you're drawing Hess cycles, you must use the data given in the questions to help you decide which type of cycle to draw. There are two types, combustion or formation. Combustion cycles look like this, with the arrows facing downwards, and carbon dioxide and H2O at the bottom of the cycle. From the reactants to the products, you have the enthalpy change of reaction, and then from the reactants and the products to the carbon dioxide and water, you have the enthalpy changes of combustion values, which will be given to you in the question. For formation cycles, you have the arrows facing upwards. So from the elements to the reactants and the products, you have the enthalpy change of formation values, and then from the reactants to the products, you have the enthalpy change of reaction value. So we've got an exam question. Enthalpy changes of formation can be determined indirectly from standard enthalpy changes of combustion. Three enthalpy changes of combustion are shown below. So we've got the enthalpy change of combustion of carbon, hydrogen and nonane, and the equation that represents the enthalpy change of formation of nonane is shown below. Calculate the standard enthalpy change of formation of nonane. So remember the definition of the enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements. So we're forming 1 mole of nonane from its elements. So we need to draw a combustion cycle because we have been given combustion values in the question. So that means that we need to have downward arrows. And on this first arrow on the left, because we have 9 carbon atoms in the equation, we need to multiply minus 394, which is the enthalpy change of combustion of carbon, by 9. And we need to multiply minus 286 by 10, because we have 10 moles of hydrogen. And we need to add these values to give us our enthalpy change of combustion for this arrow, which gives us minus 6,406. For the second arrow on the right, we have 1 mole of nonane, and the enthalpy change of combustion of nonane is minus 6,125 kilojoules per mole. So we just need to write minus 6,125. Then, if you look at these arrows, you can see that to find the enthalpy change of formation, which is this arrow up here, which is also the enthalpy change of reaction, we need to go with this first arrow on the left here, and we're going against this arrow on the right. So that means that we need to keep the sign of the arrow on the left, so that means we still have minus 6,406, and we need to flip or change the arrow on the right to positive 6,125 to find the enthalpy change of formation. So that's minus 6,406 plus 6,125, which is minus 281 kilojoules per mole. Now we have a different question. Ammonia is used to make nitric acid. The first stage of the reaction is shown below. So we have 4 moles of ammonia reacting with 5 moles of oxygen to form 4 moles of nitrous oxide and 6 moles of water. We've already been given the enthalpy change of the reaction, which is exothermic because it's negative, and it's minus 908 kilojoules per mole. Standard enthalpy changes of formation, delta HF, are given in the table. So we have the enthalpy changes of formation of ammonia, oxygen and water. Calculate the standard enthalpy change of formation for NO. We need to give the answer as a whole number. So we can start by drawing a cycle. And note that we've been given enthalpy change of formation values, so the arrows need to go upwards. Then we can label the enthalpy change of reaction, which is minus 908 kilojoules per mole. And to find the enthalpy change of formation of the left arrow, the first arrow, we need to times minus 46 by 4, because we have 4 moles of ammonia. And because oxygen is an element, it doesn't have an enthalpy change of formation, so we don't need to worry about oxygen. On the right, we have 6 moles of water, so that's 6 times minus 242, and we're going to add it to 4 of the enthalpy changes of formation of nitrous oxide, which we don't know yet, so that's our unknown value. So minus 46 times 4 is minus 184. And 6 times minus 242 is minus 1,452. Then, note the direction of the arrows. So for the enthalpy change on the top of the cycle, we're going to have to go with the arrow on the right and against the arrow on the left. So we're going with this arrow and against this arrow. So that means that we need to change the sign on the left-hand arrow, which we're going against, to positive, and the arrow on the left, the values for enthalpy change of formation on that arrow will stay as negative. So we can write this out as an equation. So minus 908 is going to be equal to minus 1452 plus 4x, which we know is going to be negative, plus 184. So So minus 1452 plus 184 is minus 1268. So then we can add 1268 to each side of the equation, which is 360. So 360 is equal to 4x. That means that if we divide 360 by 4, we get 90. So the value of x, or the value of the enthalpy change of formation of NO, is going to be 90 kilojoules per mole. Thanks for watching. Make sure to check out my enthalpy changes revision video, which should be in the bottom right hand corner now. You can also check out my website to purchase my notes and flashcards. The link should be in the description below.